In this video, we're going to discuss triple integrals in spherical coordinates. In the last video, we derived all of the formulas for converting from rectangular to spherical coordinates. And we talked about some of these ideas, but I wanted to briefly review them here before we start talking about triple integrals. But basically, the outline of this video is we'll review some of the properties of spherical coordinates. Then we'll talk about how to set up a triple integral in spherical coordinates. If you have a triple integral in rectangular coordinates, we'll talk about how to convert it to spherical coordinates. And then we'll do a couple of examples. In one example, we'll find volume using spherical coordinates. And then if we have time, in the second example, we will convert an integral to both spherical and cylindrical coordinates, and then we'll evaluate the simpler of the two integrals. Okay, so let's get started. Cylindrical or spherical coordinates are coordinates rho, theta, and phi that give us new ways of describing points in three-dimensional space. The most important thing, or one of the most important things that you need to remember about converting to spherical coordinates is what types of surfaces we get, whenever theta, phi, and rho are constants. So let's say you're given theta equals a constant, like maybe say theta equals pi over 4. What that represents is a plane that passes through the z-axis, and it lies on a line given by theta equals pi over 4 in the xy plane. Now remember, theta is the same theta that you saw in polar coordinates. So it's the angle that that point makes with the positive x-axis. So if you've got some point over here, you would look at the projection of that point onto the xy plane. You'd create a line segment from the origin out to that point, and then you would draw an angle from the positive x-axis to that line segment or ray. That is theta. So if rho and phi are free to be anything and theta is just equal to a constant, we get a plane that passes through the z-axis and it's just on an angle. Now phi in spherical coordinates represents an angle that's made with the positive z-axis. If phi is equal to a constant and that constant isn't 0 or pi over 2 or pi, those are special cases, we get a cone. The rest of the time we get a cone. If phi is an angle between 0 and pi over 2, as shown in this picture, we get a cone that opens on the positive z-axis, because these are all points that lie that many radians from the z-axis. We're going, let's say that phi equals 30 degrees or pi over 6 radians. We're going pi over 6 radians in this direction, and then the forward direction and the backward direction, in all the directions, and we get this cone. Now, if phi is an angle between 90 degrees and 180 degrees, or between pi over 2 and pi radians, the cone is going to open on the positive or the negative z-axis rather than the positive z-axis. So generally, phi being equal to a constant gives you a cone. Theta being equal to a constant gives you a plane that passes through the z-axis and just lies on a line in the xy plane that passes through the origin. Okay, now if rho is a constant, rho is the distance from that point, x, y, z, to the origin. So if rho is a constant and theta and phi are free to be anything, what you get is a sphere. And it's just actually the outer portion of the sphere. It's just the boundary. It's not a solid sphere. It's just that outside part. It's a two-dimensional surface that's occupying a location in three-dimensional space. It's like if I had a basketball and I just took out everything inside the basketball and I was just looking at the shell of that basketball, that's what this sphere would be. So if rho is equal to a constant, let's say rho is equal to 1, we get a sphere of radius 1 centered at the origin. If rho is equal to 2, we get this sphere of radius 2 centered at the origin. If rho is equal to 3, we get a sphere of radius 3 centered at the origin. Now, if I want the solid sphere of radius 3, then it's not just rho equals 3, it's rho goes from 0 to 3, and then we're going to also have some bounds for theta and phi to describe the solid sphere. So now let's put all those pieces together. If we put those pieces together for a particular value of rho, I think this picture really helped me a lot. When I realized this, when I don't know where I read it, but someone articulated this for me, it was like, oh my goodness, yes, this makes so much sense. Rho and phi act like latitude and longitude. If rho is phi is a constant, remember we get these cones. Those cones are going to intersect our sphere on a line like this. So it's going to be like a latitude line. And when phi is equal to a constant, we get a plane that passes through the z-axis. Well, if I take that plane that passes through the z-axis and I intersect it with a sphere, I get these longitude lines. And of course, rho equaling constant gets us the radius of the sphere in the first place. So I think of phi like latitude, theta like longitude, and rho like the radius of the sphere. And we put all of those pieces together to describe points in three-dimensional space. So now let's use these ideas to come up with a way for describing parts of a sphere. So let's say I've got a solid sphere of radius 3 centered at the origin. So that's my region Q. It's the interior of that sphere. If I want to describe this solid sphere, I'll need bounds for theta, I'll need bounds for phi, and I'll need bounds for rho. I know I said the wrong variables while I was writing down the other variables, but you get the idea. So if it's a solid sphere, and that solid sphere on the outside has a radius 3, rho equals 1, that's at 0, 0, 0, that's part of our sphere. And then when rho equals 2, that's part of our sphere, and rho equals 3, that's part of our sphere. We actually get all of the spheres in between, so rho ranges from 0 to 3 if we've got that solid sphere. Now theta is an angle that sweeps around the xy plane. So that's when, if I want to find theta, I look at the projection of my sphere onto the xy plane, and I think about what theta would have to go through to get the entire sphere. To get the whole sphere, theta would go from 0 to 2 pi. Now careful here, a lot of people make a mistake on this one. Phi is an angle that we're making with the positive z-axis. In order to get the whole sphere, we start at the top on the positive z-axis and we go to the bottom to the negative z-axis. So phi goes from 0 to pi. And a lot of students say, oh, why isn't it 0 to 2 pi, Miss Townsend? We don't have to go over here on this side because if phi went beyond pi, if it went to pi plus pi over 6, for example, well, that would have been measured with the 5 pi over 6 on this side because of symmetry. In order to get the other half of the sphere, our theta value is going all the way around the xy plane. So phi is an angle that sweeps down. It sweeps from the positive z-axis down. Theta is an angle that sweeps around the xy plane. And these spheres, rho is giving us spheres centered at the origin of radius rho. So if rho goes from 0 to 3, that's starting at 0 and then going all the way out to, I'm trying to draw it, or trying to show you with my hands, a sphere of radius 3. So it goes from 0 to then like a small little sphere. It's hard to do on this camera. I need to show you in person. But these are spheres radiating out from the origin. Theta is an angle that sweeps around the xy plane, and phi is an angle that sweeps down from the positive z-axis to the negative z-axis. And if you're worried about the left half of the sphere, the right half of the sphere, don't worry about that. Phi just takes care of the top part of the sphere and the bottom part of the sphere. Does that make sense? It goes from top to bottom. If phi went from 0 to pi over 2, that would be the top half of the sphere only. Okay, so that's a sphere, a solid sphere of radius 3. That's how we describe it. Now let's restrict it a little bit. Well, how would that change if we were talking about the top half of a sphere of radius 3, centered at the origin? Well, rho still goes from 0 to 3. And theta still goes from 0 to 2 pi because we go all the way around the xy plane to get the top half. If I look at the projection onto the xy plane, that projection is still a circle of radius 3. So theta still goes from 0 to 2 pi, but this time phi only goes from 0 to pi over 2. So we only go from 0 to 90 degrees to get the top half of the sphere. Does that make sense? I hope it makes sense. Now let's make one more restriction. Let's say we're just talking about let's say we took our sphere and we sliced it. We sliced it a couple of different ways. So let's say we only have the right half of the sphere. Okay. So we're only seeing this side of it. So the projection onto the XY plane looks like this. Now you're changing your perspective. So the y-axis is going up and x is going to the right, but over here x is going forward and y is going to the left. Notice that x is negative and positive here and y is only positive in this picture. So it actually looks like this because of the change in perspective, because we're changing the way we're looking at it. For this, if this is part of a sphere centered at the origin, a solid sphere, rho still goes from 0 to 3. And then when I'm looking for my bounds for theta, I'm thinking of an angle that sweeps around the xy plane. So I can look at the projection onto the xy plane. I look at this and I see that theta goes from 0 to pi. And phi, that's an angle that we're making with the positive z-axis. So theta, or phi, is an angle that sweeps down. So phi goes from 0 to pi over 2. So these are the appropriate bounds for this region. So keep all of this in mind. Now, if it's not a part of a sphere centered at the origin, then we're going to have to do some algebra. We'll have to use our coordinate conversion formulas to write the equation of the sphere in a different way. Okay, now one other thing we said was we will take a triple integral written in rectangular coordinates and write it in spherical coordinates under some conditions. And it's sort of exactly what you would expect. You're going to write the integral in spherical coordinates when the solid region of integration, oops, I guess I already said when. Because we're doing a triple integral, so it's a solid region that we're integrating over. Is a sphere or part of a sphere. There's a more sophisticated way to say this. We say when the region of integration, Q, or the integrand f of x, y, z, it sounds so fancy, exhibits symmetry about a point. What do we mean by exhibit symmetry about a point? We mean it looks like a sphere or part of a sphere, or f of x, y, z might have, the integrand might have an x squared plus y squared plus z squared, because that is x squared plus y squared plus z squared equals rho squared, and that's part of a sphere centered at the origin. So that's why we do this, that's when we do this. And yeah, we'll get into the details of how to do that in the first example. Okay, so here's our example. We're asked to find the volume between the upper nap of a cone given by z equals the square root of x squared plus y squared, and the sphere given by x squared plus y squared plus z squared equals 2z. And if you're thinking, that's not a sphere, that's supposed to be just a 2 or a constant. You're right that it's not a sphere centered at the origin, but it is a sphere. If we subtract the 2z from both sides and complete the square, we'll see that this is a sphere. It's just centered at a point other than the origin. So we've got to do a little bit of algebra first. Okay, so the best way to start this, the best way to start any of these problems is to graph that solid region that we're trying to find the volume of. So I'm going to sketch the region Q. And the way you sketch Q is you sketch these two different parts of Q. So z equals square root of x squared plus y squared. If I square both sides, I get this. Now, when I started, z was the positive square root. So I have to remember that if z is defined to be the positive square root, that means that z is greater than or equal to 0. So when they say it's the upper nap of the cone, well, that just means we get the top part of the cone. If you rewrite this so that it's in standard form for the equation of a cone, you see the z is negative, the other two variables are positive, all three are squared, and we've got a 0 over here. So that tells me I'm dealing with a cone. The fact that that negative is on the z squared term means the cone opens on the z axis. And it's the positive part only. It's not a double napped cone this time. Excuse me, having trouble talking today. So we've got that right there. So that's one part. Now this part, that's a sphere. They told us it was a sphere, but it needs to be written in standard form so that we can graph it. So the first thing that I would do is I would write the equation of that sphere in standard form. So I subtract the 2z from both sides, I get this. Then I group the z terms together. If there's a 1 in front of the z squared, and there is, I can identify b this way and start completing the square. B is -2, half of that is -1. -1 squared is +1. So we add 1 there to complete this square and add 1 to the other side. So this gives us x squared plus y squared plus the quantity z minus 1 squared equals 1. So that is a sphere. To find the center, we look at what's being subtracted from the x, the y, and the z. Nothing's being subtracted from the x or the y. So the x and y coordinates of the center are 0. Since we're subtracting a 1 from the z, the z coordinate of our center is 1. The radius squared is 1, so that means r equals the square root of 1, which is 1. So we've got a sphere centered at 0, 0, 1 with a radius of 1. I don't really think there's enough room in this picture to draw my sphere, so I'm going to draw a different picture over here. Excuse me. My sphere is centered at 0, 0, 1, and it has a radius of 1. So we're going to go left 1 and right 1, forward 1 and backward 1. Up 1 and down 1. It's not a very good sphere. That's okay. So that's my cartoon version of a sphere. That's the idea. Now we were asked to find the volume between this cone and the sphere. So there's a cone. Oops. Sitting down here below it. I'm like, is that what that really looks like? We'll see. We'll see how that works out. I hope this works. I did make this up, so we'll see. We'll see if it actually works out nicely. Hopefully the sphere doesn't actually go through the sides of the cone like that. Maybe it does. All right. I hope not, but we'll see. Okay, so we sketch Q, and then we'll say that this is the solid region Q that we're looking for, and then we want the projection of Q onto the XY plane. To find the projection, we need to set the equation of the sphere, that's the top part, equal to the equation of the cone, that's the bottom part. So I set Z1 on the cone equal to Z2 on the sphere. Ooh, and this one is actually not solved for Z. So there needs to be another way. How else can we find the equation where this cone meets this sphere? Well, I'll tell you what, we can take all of the Z's and replace them with that square root. And then we'll have an equation involving X and Y only. And that will be a set of points where the Z on this sphere is equal to the Z on that cone. So rather than setting them equal to each other, I'm just doing something a little different, just a substitution. So I replace Z on the sphere with the Z value on the cone, and I hope that it works out. That's what I do. I hope that the sphere doesn't go through the sides of the cone like that, because if it does, it's not what I wanted. Square that and that, and I've got 2 times this over here. Oops, there's a 2 on both sides. Let's divide both sides by 2. Oops, sorry. This will work out just fine. And then we can, I guess, I've got this and its square root over here. So I guess we could divide both sides by that square root. That's legal as long as x squared and y squared are not 0. And when we're on this curve, they're not. Something divided by its square root is the square root of that something. Just for example, 2 over root 2 is root 2 times root 2 over root 2. So the root 2 is canceled and we're just left with root 2. Same thing is happening here. It's just a function of x and y instead. Now let's square both sides. Oh, that's not bad. It's just a circle of radius 1. Okay. So these intersect on a circle of radius 1. That's our region R in the XY plane. Okay, so we sketched Q, then we sketched the region R in the XY plane, the projection. Okay, and now we want to find the volume between this cone and the sphere. Okay, so my volume integral in general just be the double or the triple integral over Q of dV. And I want to go from the cone to the sphere. So generally, I would let Z go from this surface to this surface. But I don't want to do that because I've got part of a sphere in my, or my region Q is part of a sphere. This would be easiest and best if we switched to spherical coordinates. So there are three things that you need to do to switch to spherical coordinates. One thing you need to do is write the bounds for Q in terms of rho, theta, and phi. The integrand, that's a 1, that stays. Now, if there was something other than a 1 there, I would need to write that in terms of rho, theta, and phi as well. And then just like before, we need a new dV. Remember when we switched to cylindrical coordinates and we said that dV was r times dr d theta times dV, or dz, excuse me. We had a different form of that. We had that extra multiplier r. It turns out that in spherical coordinates, the extra multiplier is rho squared sine of phi. If you're saying to yourself, what on earth, where does that come from? I'm going to prove it to you when we study the Jacobian in just a little bit. And of course, you can change the order of the multiplication, but this is your new dV. So we just need a description for Q in spherical coordinates, and we need to replace dV with this. And we'll prove where that rho squared sine of phi comes from once we learn about the Jacobian in the next section. It's just like that extra multiplier r that we got when we switched to cylindrical coordinates. Okay, so I need a way to describe Q in terms of spherical coordinates. And that means I need to describe all of these surfaces in spherical coordinates. Now, this sphere is not centered at the origin. So the equation for the sphere is not rho equals 1, even though it's a sphere of radius 1. That sphere is centered at 1. Or 0, 0, 1, excuse me, not 0, 0, 0. So it's not going to be as simple as if this sphere were centered at the origin. And phi is an angle. It's going to sweep. It's going to go down from here down to the equation for the cone, and we should be able to figure out what that is. And theta is an angle that goes around the xy plane. And actually, since we've seen the projection in the xy plane, let's do theta first. We get the whole solid here. It looks kind of like a snow cone. You don't just get half of a snow cone or something like that. So theta goes from 0 to 2 pi. We go all the way around the circle, all the way around the xy plane. Now, phi is an angle that sweeps. We're going to start at 0 and we're going to go down to the equation of that cone. We just need to figure out what the equation of the cone is. And that the bounds for rho are going to depend on that sphere right there. So let's figure out what those are. So we were given this as the equation of the sphere earlier. And we'd like to write this as an equation for rho in terms of theta and phi if possible. Well, given this form, it's actually pretty easy. X squared plus y squared plus z squared is rho squared. And 2 times z is rho times cosine of phi. Now normally we don't like to divide by a variable, but this time we can divide by rho. Then we get rho equals 2 cosine of phi. And if you're saying to yourself, why is it okay to divide by that? Because the danger in doing that is that rho might be 0. If rho is 0, then 0 squared is equal to 2 times 0 times cosine of anything. But it's possible that this equation also describes the case when rho might be equal to 0, and it does. If phi is equal to pi over 2, we get 0 here. So this doesn't exclude the case rho equals 0, so we're good to divide it out. Like this is equivalent to that. because it includes the rho equals 0 case. And rho equals 0 is that point at the origin, 0, 0, 0. So we're good there. So this is one way to describe the sphere. So now you're thinking to yourself, okay, what are my bounds for rho? Well, rho equals 0 is part of our surface. And then we go out to that sphere. So rho goes from here to here. So rho goes from 0 to 2 cosine of phi. So that means we have to integrate with respect to rho before we integrate with respect to phi. Now, we said earlier theta goes from 0 to 2 pi because we go all the way around the xy plane. Now we need to find bounds for phi. Okay, to find bounds for phi, we're going to look at the equation of the cone. So here's our cone, and I'm suggesting that this will give us the bounds for phi, because when phi is a constant, we got cones, like that's what we saw. If we have a constant value here for phi, and we go exactly that number of radians in all possible directions, we get a cone. So I think this is phi equals a constant. Let's figure out what that constant is. Well, to do that, we're going to substitute. Remember, z is equal to rho cosine of phi. And x squared and y squared, or x and y, can be written in terms of rho and phi and theta as well. And there's not enough room on here, so I'm going to use another sheet of paper. So we've got z equals the square root of x squared plus y squared. And z is rho cosine of phi. And x is rho sine of phi cosine of theta. Y is rho sine of phi sine of theta. Now we want to square that. Square each factor separately. Whoops. So you get rho squared sine squared phi times cosine squared theta plus rho squared sine squared phi times sine squared theta. And it looks really bad, but it simplifies quite nicely. Look at that term and that term. What do they have in common? I hope you said rho squared sine squared phi. If you did, you were right. So we'll factor that out. And then we're left with cosine squared theta plus sine squared theta. Hey, there's one of our favorite Pythagorean identities. It simplifies quite nicely. It's gone. Just a 1. Isn't that nice? And rho is always non-negative, so the square root of rho squared is just rho. And phi is between 0 and pi, so sine is positive, or actually non-negative there. So the square root of sine squared phi is sine of phi. And we can divide both sides by rho. Well, actually, we probably shouldn't. Let's subtract. Well, okay, yeah, we'll subtract this from both sides. So this tells us that either rho equals 0 or cosine of phi minus sine of phi equals 0. Or alternatively, sine is equal to cosine. Now you know from trig, there's only one angle where the sine and cosine are the same. Well, there's a family of angles. That angle would have to be pi over 4 plus as many multiples of 2 pi as you want in either direction. But phi is always between 0 and pi, so that's the one we're looking for. It's pi over 4. And you can also see from the picture that we're not going more than pi units away. We're just going pi over 4 units. It's 45 degrees. It's nice. So we start at 0, because phi equals 0 is the positive z-axis, and then we go over here to phi equals pi over 4. And we're going to put all those pieces together now. And actually rho equals, or phi equals pi over 4 does include this case, so I really don't need that. So here are our bounds. We said rho starts at 0 and goes to 2 cosine of phi. Phi goes from 0 to pi over 4, and theta goes from 0 to 2 pi. Let's look at our pictures and make sure that that's consistent with our intuition. So we said rho goes from 0 to 2 cosine of phi. That means rho goes from the origin out to this sphere, the sphere of radius 1 centered at 0, 0, 1. That's what we're talking about. Meanwhile, theta is an angle that sweeps around the xy plane. We get the entire thing. When I look at the projection of my solid onto the xy plane, I get a circle of radius 1. So I can see from this circle, theta starts at 0 and goes to 2 pi, so I'm good there. And then lastly, we've got pi over 2, or excuse me, phi, which goes from, I don't know why I said pi over 2, it's phi, which goes from 0 to pi over 4 right here. I was thinking of half of something, half of that pi over 2, but it's pi over 4. So phi goes from 0 to pi over 4. So those are our bounds. And I told you without proof, and we'll prove it later, that dv is equal to rho squared sine of phi times d rho d theta d phi. And of course, you could change the order of that multiplication because that's how multiplication works with real numbers. Okay, so now we have everything that we need to set up the volume integral. Volume is the triple integral over q of dv, which can be written this way. Now rho depends, the bounds for rho depend on phi, so we have to integrate with respect to rho before we integrate with respect to phi. So I'll integrate with respect to rho first. And then let's integrate with respect to phi. So let's let phi go from 0 to pi over 4. And then we'll let theta go from 0 to 2 pi. And dv is not just d rho d theta d phi. It's rho squared sine of phi times d rho, integrating with respect to rho first, then d phi, because of that choice of the order, and then lastly d theta. Okay, cool. Remember what we're trying to do. We're trying to find the volume of this guy. Now that we've set this up, we just evaluate the innermost integral and work our way out. So we're anti-differentiating this with respect to rho. So at this point, as far as we're concerned, sine of phi is a constant, so we should take that out. The antiderivative of rho squared with respect to rho just comes from the power rule. Add 1 to the exponent and divide by the new exponent. Then substitute in rho equals 0 and rho equals 2 cosine of phi and subtract. So we anti-differentiate with respect to rho, and then we use the fundamental theorem. So I've got 1/3 sine of phi, and this will be 2 cosine of phi, quantity cubed, minus this expression evaluated at 0, which is 0. And then we integrate with respect to phi and then theta. So then you cube this piece and that piece. So it's going to leave me with an 8 times cosine cubed. I think I'll take out that 8/3. Let's factor it out to sort of get it out of the way. You don't have to, but it makes it a little cleaner. Now I've got cosine of phi, quantity cubed, times sine of phi, d theta. Now you don't have to write it that way, but I chose to write it that way because it reminds me that the most appropriate way or the easiest way to evaluate this is to do a u sub. I actually can't think of another way. We've got to do a u sub to evaluate that integral. And u is the function nested inside another function. So as soon as I see those parentheses, I know that's got to be my u. So I let u equal cosine of phi. Let's compute du. Derivative of cosine is negative sine. Don't forget your d phi. Multiply by -1. Okay, and then we need new bounds. So I evaluate my u function at 0 and pi over 4. At pi over 4, we get cosine of pi over 4, which is square root of 2 over 2. At 0, we get cosine of 0, which is 1. So I still have the integral from 0 to 2 pi out here. And I still have that 8/3. And then I need to take this integral and write it entirely in terms of u. Notice, new bounds are 1 and square root of 2 over 2. Then I have u cubed, and sine of phi d phi is negative du. So I have a negative du times u cubed. Oops, negative du times u cubed. And don't forget that 8/3, it's still there. And we're evaluating all of this. First, we're integrating with respect to u, and then we'll integrate with respect to theta. So you can factor out that negative if you want to. You don't have to, but you can. Then you anti-differentiate this by adding 1 to the exponent and then dividing by the new exponent. And then you substitute in the upper limit for u and the lower limit for u, and you subtract. So I've got 1/4 of this, so that's negative 2/3 out front. And then I've got times u to the 4th. So that's square root of 2 over 2 to the 4th minus 1 to the 4th. And we're integrating. You can factor all that out as a constant. So now we're left with the integral of 1 with respect to theta from 0 to 2 pi. The antiderivative of 1 is just theta. And we can do some arithmetic over here. 2 to the 4th in the denominator is 16. Square root of 2 to the 4th is square root of 2 times square root of 2, which is 2. 2 times 2 is 4. And then we're evaluating from 0 to 2 pi. Okay, so that's our answer. So we've got negative 2/3, negative 3/4, and 2 pi. The 3's reduce, the 2's reduce with the 4, and we just end up with a negative times a negative times a pi. We get pi. Huh, that's cool. I love pi. That's the volume of that guy. Who knew? Okay, I think I'm going to save the next example for one last video over volume, not because we can't tag it onto this video, but because I think this is a good stopping point. We'll do one last example with cylindrical and spherical coordinates and triple integrals, and then we'll be done with this material, and we'll go on to the Jacobian next week.